I wonder who that lady is who says that. Recording in progress. She sounds so serious. All right, so I'm going to go ahead and run over the first little bit of this again so we have a rather complete picture. I might edit this out a little bit later, but probably not. All my mistakes and everything will be there. So chapter 1 is all about data types, among other things. And different data types really mean different tools are needed. And from our perspective, it really falls into two categories: number stuff and thing stuff. Height and weight, number of cars, number of TVs you own, those are all number things. Your favorite color, your political party, any sort of survey data, anything like that, any sort of opinion data, these are all things. That sounded funny, but that's the truth. They're things. Excuse me. So as I was saying before I turned on the record button, we like to refer to things as categorical or qualitative data. Quality, category. Numbers, on the other hand, could fall into a couple of different categories. Discrete variables, those are the kind of numbers that appear only a finite number of times or a finite number of ways, or they are countable. Don't worry about this countable stuff. That's honestly a super duper advanced math concept that we really don't need. What we need are more examples of this. Let me give you another example of discrete. Soda choice. You could choose an 8-ounce, a 12-ounce, or a 16-ounce soda. If you go to Burger King or McDonald's or someplace like that, you have a finite number of choices. Now, that is discrete. Let me give you an example of something that is not discrete. Here's something that's not discrete. Height is not discrete. I have a son. He is, he's almost 9 years old. He used to be real little, like about an inch tall, I guess. But he's been growing ever since. And now he's much bigger, much bigger. He's off to parkour right now. And if he's here at, I don't know, I'll say 4 feet. And here he's at 4 feet 6 inches, which is his height right now. As he grew from the 4 to the 4 feet 6 inches, he had to pass through every number on the number line between 4 and 4.5 feet. He didn't jump around like we do with the soda choice or the shoe size. So every value in there was at some point attained by my son when he grew between 4 and 4.5 feet in height. So continuous data. So a continuous variable can assume any value on an interval. Any value on an interval. Common examples are most, not all, but most physical quantities. So those are things like height, weight, time. Any one of those could be measured ever more finely given better and better instruments with no end in sight. It is truly on a number line, your measurement could assume any value on this interval, any value on that interval at all. Sometimes the endpoints are included, sometimes they're not, but the point is any value on that interval could be obtained. So we have this differential, if you will, in data types. And this is the picture I actually have in the website, in the Canvas shell. We can take our data and we can split it up into the qualitative, or the, as I like to call it, the quantitative. That's the number stuff. The quantitative can be split between the discrete and the continuous. And this is the way we like to divvy up our data. And very easily, a nice way to keep them straight is really to go back to some of that stuff I was saying before. Your qualitative data, these guys here, that's really good for stuff and things. Things and stuff where counting really isn't the issue. Number stuff, quantitative, discrete. These are things you count, things that you count with your fingers, perhaps, or a 10, 10 and a half, 11, 11 and a half sort of cadence. The continuous, this is more things you must measure. And I will point out that these are not really super hard and fast ways of thinking here in the brightly colored pink. But they really do help students get a handle on these things. What I really need students to be able to do is to not regurgitate definitions. That would be easy enough as it is. We have open book, open note exams and quizzes, but to be able to recognize these types of things when they appear. Give me a moment, and I'm going to come up with an example or two, and I will point out exactly what I mean by this sort of thing. So, all right, so here's a really good one, and I do like this one. I'm surprised I didn't remember it off the top of my head. I saw something that reminded me of it. So think of clocks. All right. Digital clock and an analog clock. So think of clocks. It's definitely a number. How long? How long? How long will I continue to talk? How long until class is over? Things like that. Quantitative. There's a number there. Now, if you have a digital clock, what do you see on your digital clock? You see something like a 1, a 2, a 3, and a 4 with a dot there. So maybe it's 12:34. There's a little bit better. What do you see on an analog clock? It's a little bit after 12, so the little hand's there. It's a little bit after 12:30, so the big hand's down there. We've got the 6, we've got the 12, we got the 3, we got the 9. Now, what's the next number you're going to see on your digital clock? The next number you're going to see is 12:35. You're not going to see anything happen between 12:34 and 12:35 on Mr. Clock, not Mr. Digital Clock. That's because when we tell time with a digital clock, it is discrete. On the other hand, this guy here, he's been measuring time continuously. He doesn't jump around, he moves constantly. So you have continuous for your analog clock. Most of my students do really, really good with everything except the notion of discrete. You guys get a little bit thrown by discrete. Sometimes you combine it with continuous or try to combine it with qualitative, but it's a very subtle definition. That's why. It's the most mathy definition that we've seen so far. It's truly big boy and girl arithmetic. Now, let me put the data aside for just a bit and jump back into some very basic vocabulary. Because we're going to start using this kind of data. And I need to have us have a bit more vocabulary underneath our belt. We're going to be taking measurements, whether it's of things or numbers or physical quantities. We are going to be gathering data. So, more about data. And I use these words literally all semester long. It's hard for me to think of two more important words than the ones I'm about to use. The first is the word parameter. If you look it up in your book, if you find it online, it is a numerical measurement it's a numerical measurement that describes a characteristic of, and this is the important part, a population. I need to have you associate the word parameter with a population. Now, in almost all cases, knowing the exact value of a parameter is going to be an impossible task. Populations are humongous. Let me give you an example. Suppose we wanted to measure the average height of everyone in America right now, today. I could set out on that task, go from coast to coast, Hawaii, Alaska, even our territories and whatnot, like Guam, the Virgin Islands, Puerto Rico. But here's the thing, by the time I was done measuring everyone, supposing I could, half those, well, I don't know about half, but a number of those people would have kicked it. They would have died, they would have moved on. Furthermore, there'd be a whole bunch of people that were born in that process of gathering all that data. Wouldn't have any data on them at all. So the notion of a parameter as a numerical measurement is something that is always a bit unobtainable. Doesn't mean it doesn't form a nice component of study, though. Now, the next word is statistic. This is a numerical measurement. And it describes a characteristic of a sample, not a population, of a sample. Maybe you notice that the definition is like essentially identical for the two things. A numerical measurement describing a characteristic. But a statistic comes to us from a sample. The statistic is the one thing we know. We went out, we got a sample, we measured the sample, up one side, down the other. We know everything there is about our sample. We have statistics. I have the average height, the average weight, the average age of everyone in a sample, perhaps. But I know that for everyone in the sample. So here's the way the two things play together. And they don't really play together. It's kind of like the parameter just sort of ignores the statistic. So, so we use statistics. No, let me rephrase that. I don't like the way that sounded. There we go. We use a statistic to estimate a parameter. So I didn't spell that right. Don't look. So we use that statistic to estimate a parameter. Remember, populations are very, very large. It has an unknown parameter. My sample is very small. My sample has a known statistic. I know what that is. I have no idea what the parameter is, but I know exactly what the statistic is. What we want to be able to do is to extrapolate and take from the sample. We want to take that statistic and use it to estimate the parameter. And so it should be pretty clear that this is some sort of guessing game that we're going to be involved in. And that's really how this works. So where's my list? Here it is. I'll bring this back over. So our sample data will be qualitative sometimes, quantitative at other times. It could be discrete, perhaps, or it could be continuous. But, excuse me, it will generate a number of different types of statistics. And we'll use those to estimate different parameters. How do we keep stuff straight? It's really important that we do this semester. I will point out that parameter in population versus statistic and sample. So you can see Those begin with a P. These guys begin with an S. PPSS. So they go together letter-wise. Sometimes that helps students keep things straight. Sometimes it helps teachers keep things straight. In any case, parameter is a population value. Statistic is a sample value. Parameters are really, truly difficult to get a handle on. Your sample statistic is very easy to find. It's what you work for when you do statistics. All right, let me go ahead and just talk a little bit about a second type of measurement. And there's a couple of different ways to organize our data. And that one that we just got done looking at is one way of doing it. Here is another alternative, and I really don't stress this, so I'm going to mention it once and I'll never mention it again. It won't appear, or it shouldn't appear anyway, as any homework question or any quiz or exam question. But there's what we call the levels of measurement. Nominal is the most basic level of measurement. Those are things that just have categories only. The next level is what we call ordinal, which means you can attach a number to it, but the numbers have no real numeric meaning. They can be put in order, but you can't come up with a meaningful difference. And I'll give you an example of that in a moment, perhaps. Interval, this has got a bunch of number stuff in it, and most of the math works the way you would expect it to. In fact, all the math works the way you would expect it to, but there's no natural zero, which sounds really, really odd, which is why I don't stress this particular method except this one time. And finally, ratio. Ratio is a pure numeric value where zero means zero and differences have meaning. Let me give you an example what I mean from ordinal. So let's see. Jerry Rice was number 81. Montana was number 16. They've got numbers on the back of their jerseys, but are their numbers really, really numbers? No, not really. They're really there instead of a name. They're kind of like an extra name. You can do math with them, but it doesn't mean anything. So let's see, 81 minus 61 is 75, 65. So 65 what? Means nothing. But at the end of the day, levels of measurement are in there too. I feel compelled to talk about it just a little bit, merely because it's in the book and it does confuse people. They try to apply it, but I really just leave it alone. That's something that's much easier to get across, by the way, in a face-to-face class. Now I want to talk a little bit about sampling methods. Samples. Samples are the most basic building block of anything in the land of statistics. The selection is most important. It is truly the most important component of any statistical study or analysis. Math is math and it's number stuff. And number stuff really knows nothing about whether a sample is a good sample or a bad sample. We do have a general goal. We want We want what we call a representative sample. What that means is it mirrors mirrors the population under study, whatever it might be. So there's a couple of different things to keep in mind about sampling. And I'm going to bring out some definitions, and one of them, the first one anyway, is a little bit tedious. But I do want to run through different types of samples, and then we'll go on from there. So the most basic type of sample is what we call a simple random sample. And we use this often when we're pulling from a big population that has no real overlying or underlying structure or context. And you'll see what we mean by that as I go through these examples. But a simple random sample. Now, this is a very, very technical definition. And it really means something in the land of probability. But what it says is that each sample of a given size has the same chance of selection. So the question is, what does that mean? And I'll give you a nice example, or a reasonable example. Suppose we've got a population, and my population's a little odd here. I'm not sure what I'm measuring, but I know that I've got 4 members in my population. It's a very, very small population. I'm not going to give you any number notation, but N for this population is 4. So my sample is going to be size little n equals 3. So I'm going to dip into this population and I'm going to pull out how many? 3. There's a number of different ways I could do it. I could get a 4, a 9, 11. I could get a 9, 11, a 14. I could get a 4, 11, 14. I could get a, let's see, 4, 9, 14. And finally, I could get a 4, 9, and 11. 1, 2, 3, 4, 5. I think there's one more in there. I think a 9, 11, and 14 are the last one. So there's all these different samples that I might get. All of them. And which ones will I actually get, or which one will I actually get? I don't know. But I do know that they all have the same chance of selection. So any one of these has the same chance of being selected as my sample. That's what we mean by a simple random sample. That's a difficult thing to hang your hat on at the start of a semester. But it is kind of the gold standard. Now, there are variations on that simple random sample, and they have to do with what is being actually sampled. We have a couple of different types of sampling methods. Students need to be able to identify them, or perhaps offer up an example. So your types of sampling methods really sort of depend on what it is you're trying to sample. I'm going to start with systematic sampling. We pick a random starting point, then select every, and I'm going to use, I think the book likes the letter K, every kth item. That's an example of systematic sampling. Here is your real world example. Is the assembly line. So things come down the assembly line, and maybe we're going to select every third one. So K equals 3. So we're going to take that one, and that one. Where are you? There you are. For testing. Maybe they're Porsches. Maybe they're going to run them into a brick wall and make sure no one dies. So, systematic sampling. Next up is something called stratified sampling. Stratified sampling means your population is divided on characteristics, and samples from each characteristic are taken. Probably simple random samples. But think of this, if we're studying gender, for example, we might have sample 1, male, sample number 2, female. If we're working here at Hartnell, it's declined to state on some of our forms, whatever it might be. We would take 1, 2, 3 distinct samples. The idea being, if you've seen strata of rock, you sample from each of the different layers, so to speak. Stratified sampling. One of the more subtle, but it gets used a lot in various ways. Is what we call cluster. Cluster sampling. This is truly, I think, the wordiest, maybe even wordier than the simple random sample definition. But cluster sampling means that we partition a population into clusters or groups. And that's the first part. Then what we do is we randomly select some clusters or groups. And then we make sure we go ahead and you count all members in those selected clusters. So how does that actually work in practice? What does that mean? This is kind of a weird definition. I saw this. Happen over at. I think it was the. No, it was the Simpkins Center up in Santa Cruz, the Marine Mammal Center, but it does some other things. um, if you take a tide pool, they're kind of oddly shaped. What they have up there is they have these grids. There's a wooden frame, and the grid is made out of, I think it's rope. And what they do is they lay it down on top of a tide pool, and then they randomly select some of these clusters. So those are some clusters there. And you randomly select one and perhaps count, oh, I don't know, starfish, if that's what you are studying, perhaps. But that's the idea of cluster sampling. I'm going to give you another example. If we take city blocks, they form natural clusters. We might randomly select some of these city blocks and measure rent for all that live in those selected clusters. And it really gives a nice sort of way to do certain things. I'll let you read more about those, but this is one of the more difficult ones. There is one that's really easy, and who uses it? Only the unscrupulous. Convenience sampling. Now, let me give you a hint here. Is it a good idea to do your major shopping at a convenience market if you don't have to? Probably not. Convenience sampling is the same thing. Just say no. Convenience sampling is exactly what you would expect. We use data that is easy to get. There's a couple of examples of common examples of convenience sampling. The biggest one that comes to my mind is the self-selection type of poll. Call in if you support or perhaps don't support blah, 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 blah. You can't get a representative sample via a self-selection poll. That's an example of convenience sampling. It's data that's easy to get, and it means nothing. You see it all the time or hear about it all the time on radio, internet, TV shows with call-in polls. Oh, I suppose they're entertaining at some level, but in terms of determining actual actionable statistical data, no. So that kind of brings me to the end of my discussion here on that particular topic, the topic of data types and sampling methods. Let me jump back to my other screen. There we go. So there we are. We'll have more of this kind of thing next week and off until the end of the semester. You can look for this posted sometime tomorrow or the next day after that. I've got to go through and do at least some cleanup on the closed caption stuff. It gets translated, but oh my God, some of the stuff is just nuts. So I need to take care of that. In any case, I'm going to let you go now, and you have a nice weekend. I'm not going to be around on Monday. Monday is Labor Day, so I will not labor, and neither should you. I'll pick my office hours up on Tuesday. That would be Tuesday 4 to 5. I'll see you all then. If you have any questions, just shoot me an email, and we'll go on from there. Thank you, and goodbye. Oh, there we go. Goodbye.